Good morning and welcome to NASA's Jet Propulsion Laboratory. Today is L-1, that's landing day -1, and everyone is getting more and more excited as we get closer to the landing of the Mars Curiosity rover tomorrow at 10:31 p.m. Pacific time. I'm going to introduce our panel from the mission team. They're going to explain a little bit more about what to expect tomorrow night, and we'll start with Doug McQuistion. He's from NASA headquarters, and he is the Mars Exploration Program Director. Arthur Amador from the Jet Propulsion Laboratory. He is the mission manager for the Mars Science Laboratory. Steve Sell, also from JPL. He is on the Entry, Descent, and Landing team. Richard Cook from the Jet Propulsion Laboratory. He's the Deputy Project Manager of the mission. And Ashwin Vasavada, also from JPL, the MSL Deputy Project Scientist. And we'll begin with Doug McQuistion.
Thank you, Veronica. 1 day, 12 hours, 59 minutes, 45 seconds. Who's counting? Anyway, it gets scarier every day. So I want to start actually with something a little different here this morning. I'm going to start with what's going on with the orbiters. So Odyssey's in good shape. I mentioned at a press conference 2 days ago that it was now in position to collect the telemetry and beam it back to us in a bent pipe mode. MRO started its EDL sequence yesterday. And what I want to show is a quick animation of what at least MRO is going to go through to cover the MSL entry. So if we can bring this first animation up. What you're seeing is video imaging of MRO. The red vector is the -X of the spacecraft. What's important is the green vector, which is the pointing angle of the high-rise imager. And you'll notice the spacecraft flops around quite a bit. This is both to keep the sun in line as well as pointing down. You see MSL coming in the pink as it lands, and we're going to attempt to have high-rise point at MSL in its final phases of descent and get an image of it going down. This is going to be difficult. As you can see, the spacecraft does a lot of gyrating related to gymnastics, if you will, since we're in the Olympic season. But it's a pretty challenging thing that it's doing. The team's worked really hard, and the Odyssey team has worked equally hard on their system. So these guys and gals and their spacecraft are ready to do this. And I really hope we can get this image, but it's going to be tough. We were really lucky on Phoenix getting that one. We'll see if we do it this time. So that's kind of a fun video. Back to MSL. Like all missions, MSL started with something that was pretty scary and pretty risky, and that was called launch. Unlike most missions, we haven't finished the scary and risky stuff yet. MSL still has to put Curiosity on the surface after it goes through the atmosphere. Our 7 minutes of terror, which you'll continue to hear about. So can we do this? Yeah, I think we can do this. I'm confident. The team's done an amazing job. We have the A+ team on this. They've done everything possible to ensure success, but that risk still exists. It's going to be tough. If we're not successful, we're going to learn. We're going to learn from this. We've learned in the past. We've recovered from it. We'll pick ourselves up. We'll dust ourselves off. We'll look at this and do something again. We'll do it again. This will not be the end. Human spirit gets driven by these kinds of challenges, and these are the kind of challenges that force us, drive us to explore our surroundings and understand what's out there, and obviously look at why are we alone. Let's bring up this next graphic. But to tell you how hard this is the scoreboard. We are behind. Mars has been winning. The global success rate is about 40%. This is orbiters, landers, flybys, etc. So it's tough. This is the most challenging landing we've ever attempted. So we'll see how this goes. We're all looking forward to it. I'm confident. I'm proud of this team and what they've done, and I'm proud of their readiness. It's pretty exciting. So at the end of this little talk on Phoenix, I quoted a Rolling Stones item. So to continue that tradition at this point, I'm using Tom Petty today. So we're learning to fly and we don't have wings. Getting down is the hardest thing. With that, over to Arthur.
No problem. Okay. My name is Arthur Amador. I'm the MSL Cruise EDL Mission Manager, and I'll give a quick summary of our current status, recent events, and upcoming operational activities. So regarding our current status, we're at entry minus 36 hours. The spacecraft and ground systems are all healthy and performing as expected. The spacecraft is now in the EDL approach configuration. In our final approach orientation, pointing our medium gain antenna within a degree of the Earth, we've got a strong telecom signal receiving data at 2,000 bits per second over the DSN antennas of Madrid as we speak. The power subsystem is healthy. Our rover batteries are charged to 100%. The thermal and propulsion systems are nominal with stable temperatures and pressures. And the DSN continues to perform well, tracking the spacecraft continuously and conducting 2 differential ranging passes per day. Can I get the graphic, please? So with a little under 4.5 million kilometers to go to reach Mars, we've traveled now 560 million kilometers around the sun since launch 8 months ago. And we're now right on target to fly through the eye of the needle. That is our target at the top of the Mars atmosphere. The target is a box that's 3 kilometers by 12 kilometers in dimension. And we're flying right through it. Okay, thank you for that graphic. Events over the last few days on the spacecraft have been nominal and quiet, as nominal and quiet as we could have hoped for. The spacecraft has been under the autonomous control of the onboard EDL sequence since Monday evening and has been executing its actions as planned. Our trajectory inbound to Mars has been right down the pipe, so we canceled last night's opportunity to perform our 5th trajectory correction maneuver. During the hours that we have left here before landing, the flight team will remain vigilant, monitoring and assessing the health of the spacecraft and tracking its trajectory and preparing any necessary changes to guidance and entry parameters. We have several opportunities to make final parameter updates, 1 today and 2 additional opportunities tomorrow if we need them. We have 1 more significant activity to perform with the spacecraft late tonight, and that's to command the final enable and activation of the contingency software on our backup computer. The team's confident and thrilled to be finally arriving at Mars. And we're reminding ourselves to breathe every so often. Our system's in place, and we're ready to go. So I'll pass it on to Steve Sell and the EDL team.
Good morning. My name is Steve Sell. I'm on the entry, descent, and landing team here at JPL for Curiosity. And like Arthur, I just have to keep reminding myself to keep breathing. Only got 36 more hours to go. And so I just want to walk everyone through what we can expect to see and hear tomorrow night as we go through entry, descent, and landing. As you remember, because we've probably been talking about this for quite a bit over the past few days, there's several different phases of EDL. And at first we enter the Mars atmosphere. We're going about 13,000 miles an hour when we do that. And as we slow down with the initial drag on the atmosphere, that's what we call the entry phase. And during that time, we're doing our hypersonic guidance maneuvering. So we're basically carving back and forth through the atmosphere to control how fast we're slowing down, to get ready to deploy the parachute at about 1,000 miles an hour, and then we're on the parachute for a while until we get a good radar solution on the ground. Once we get that radar solution on the ground, we wait until we're about a mile off the ground, and then we cut free from the parachute, do our powered descent, and finally ending in the wonderful sky crane maneuver where we lower the rover on 3 bridles underneath the descent stage and set it gently on the ground. And the descent stage then flies away to a safe landing about 500 meters or so from where we place the rover. So, like you all, I'm going to be, eyes peeled to the monitors for this whole thing. And so I just want to tell you how we're going to be watching this. And we actually have 4 different ways that signals are coming back to Earth. And so there's a lot going on here. I'll try my best to explain it pretty clearly. Just thought at first I would point to some things on the spacecraft here that are of interest for the communications during entry, descent, and landing. The first is this antenna that's tilted out the side of the parachute cone here. That antenna will be transmitting on the X-band, and I'll get into that in a little bit, but that will be transmitting tones back to Earth, and we've We've used those in the past in past missions. And there's an antenna that wraps all around the parachute cone here, and that will be transmitting on the UHF frequency, and that will be transmitting data back to Earth, or to the relay orbiters that Doug mentioned before. So the tones are basically a series of beeps from the spacecraft. We don't actually hear them as tones in the control room. We actually just see them appear as numbers on the screen, but there's no actual information or data transferred in those tones. They're just markers of, I've gotten this far in the entry, descent, and landing sequence. The UHF is a more rich data set. Then we can actually send numbers back, so we get things like altitudes and velocities, positions, and more rich data like that. So how this will play out on EDL night, tomorrow night, we actually have a unique timing where we've tweaked the orbits of the Odyssey spacecraft and the Mars Reconnaissance Orbiter so that they will pass over the landing site as we're landing there, and we'll use both of those to relay our UHF data back at different timescales, and I'll get into that in a second. But if we could bring up the first video, it demonstrates the sequence of events as we're approaching Mars. You can see MSL there with its leaving a little trail as it's coming in. So Gale Crater appears on the right of the screen. You'll see it marked there. So this is coming in from the west to the east, and you'll see MRO will pass over the landing site from the south to the north, and you'll see Odyssey come in from the north to the south. You'll see it in a second, and MSL is just about landing. It touches down almost when MRO is directly overhead, and Odyssey is passing off a little bit more to the east. So that's the timing that we're using to cover entry, descent, and landing. And the way we're using both of those spacecraft is Odyssey is operating in what we call a bent pipe mode, which allows us to relay data back to Earth in real time. So that's what we're going to be glued to on the computer screens. Everybody's going to be watching that, and we're using that to drive some pretty cool animations that will show the telemetry in graphical form as it comes back. So you'll actually see pictures of the capsule and the parachute and stuff like that, and we'll actually be able to watch the telemetry in a meaningful way as it's descending. The tones actually will start transmitting those about 10 minutes before entry into the atmosphere, and those tones are direct to Earth, so they do not get relayed through the orbiter. The tones will keep being emitted by the spacecraft all the way down to until we're on the parachute. At that point, the Earth actually sets from view of the spacecraft, and so we will no longer be able to receive the tones. Although the spacecraft will still be sending them, we're kind of blocked from view. However, Odyssey passing overhead will still continue to relay that high, rich data set back to Earth all the way through touchdown and for a few minutes after touchdown. In addition to the tones and MRO and Odyssey, we will also be making use of the European Mars Express spacecraft, which will be recording the UHF signal, and it will send what it hears back to Earth several hours after landing. And I know there's a lot of stuff going on here, so we put together a little video to try to help explain the sequence of the different timings. So if we can have the second video, please. You'll see the spacecraft entering there, emitting the Aquaman UHF tones and the little magenta or pink the pink tones direct to Earth. And you can see MRO and Odyssey passing over the capsule as it's landing, and when Odyssey gets into view of the UHF, it then relays that back to Earth. And MRO will record that UHF data and play it back a couple hours after landing. And there you see the DSN receiving that information for us to view here at JPL. And so, as I said, we expect to have the Odyssey bent pipe relay to us all the way through touchdown, through several minutes after touchdown. And then at approximately an hour and a half after landing, Odyssey will replay that data again back to Earth, everything it heard, just as another way of getting the data back again. MRO will replay what it heard back to Earth, and that replay will start that replay will happen several hours after landing, and the data will actually be available to us. We have to go through a slight decoding process once we get that data down, but we'll have that about 10 hours after landing. And I have to say that I'm extremely excited to be watching all of this through whatever data we get on the screens here, and I can't wait for all of us to see it happen tomorrow night. And with that, I'll turn it over to Richard, who will walk you through what's happening after touchdown.
Okay, well, good morning, everybody. I'm Richard Cook. I'm the Deputy Project Manager. I like the tractor beams in the video. That was cool. So I'm actually going to talk about what occurs after landing. And of course, you know, the big difference between cruise, as we are right now, and once we land is that our ability to communicate with the vehicle and to see what it's doing all the time changes. We can do that during cruise because we have, at this point, continuous deep space network tracking, but once we're on the surface, it changes pretty dramatically. Part of that's because, to be honest, we don't know exactly, well, Steve told you what the plan is for landing, for communications. Clearly, there are situations that will occur or potentially may occur during EDL where we won't be able to get that communications all the way down. Some of them we know about when the vehicle separates, for example, the rover separates from the descent stage. But in addition, there certainly are situations that might come up where we will not get communications all the way through. And it doesn't necessarily mean that something bad has happened. It just means that we'll have to wait and hear from the vehicle later when it gets opportunities to communicate with us in the subsequent day or hours and days following that. So what I'm going to talk to you about first is really those communications opportunities that occur right after landing and what we expect to see during those opportunities. So if we start with the first slide, and I have to show view graphs because I'm an engineer, I guess, and so here's my view graphs on what we expect to see in terms of communications opportunities on August the 6th, clearly after we land late at night on the 5th. The first opportunity for hearing from the vehicle is the one that Steve referred to, which is actually during the landing itself. And we do expect Odyssey to remain visible from the rover from anywhere between 2 and 5 minutes after landing. And during that time, we should get some engineering data. We hope to get an indication that the spacecraft transition mode into what we call the surface mode, out of EDL into surface mode. And it's possible we also might get some images as well, and I'll come back and talk to you about that in a second. But because of the geometry that Odyssey is in, you saw from the video where it flies over kind of off to one side of the rover, it turns out we actually have a separate Odyssey opportunity later, about 2 hours later that night. And so it's at 12:30 in the morning is when we expect to get that second pass. It'll again be about a 9 or 10 minute overflight. And hopefully by that point we are essentially done with all of the first set of activities we wanted to do on the first day of after landing. It's we land basically at about 3 o'clock, 3:30 on Mars, and so this rover has another hour, an hour and a half of activity to do, and then the Odyssey overflight will occur, and we'll basically be done with the things we expect to do. That Odyssey overflight will be the next opportunity to get some pictures back. And again, I'll talk a little bit more about this in a bit, but we are in both of these two overflights that late morning, or late evening rather, early morning, we expect that we might get some black and white fisheye lens HazCam images. And I do have the rover here in case you guys are wondering what cameras we're going to be taking pictures of. They're from the HazCams that are on the back of the vehicle here, and they are black and white. We might get, they have covers on them, and so we might actually get images from the first pass and right after landing through those covers. The covers are actually transparent, but then we'll actually deploy those covers and we'll take some more pictures, and so we may see those images in the second Odyssey pass that occurs late at night. Then basically the way that the Mars and the orbiters work is that the spacecraft or the rover is sitting on the surface and the orbiters continue to go around, but they're not lined up with where the vehicle is. And so we have to wait 12 hours essentially for Mars to rotate under the vehicle, under the orbiters, and then we'll get our next opportunity to communicate. And because we have two orbiters, we get two almost at exactly the same time the next morning here on Earth, 11:30 in the morning, 11:40 in the morning for Odyssey and for MRO. And so again, that would be the next time where we would hope to hear from the vehicle. And again, depending on what has happened during EDL, as well as what happened in those first few minutes after landing, this could be, in fact, the first time we hear from it, depending on what has occurred. So those are the overflights from the orbiters. In addition, we have the ability with the rover using its high gain antenna, you see here, to communicate, and its low gain antenna to communicate, which is right here, to communicate with the Earth directly to the Deep Space Network. And so because that's a very much farther distance, the vehicle's transmitter is not that strong, we don't actually expect to get data from that communication path, but what we do is what we call a beep, which is a little bit like a tone during EDL, where the vehicle essentially just transmits a signal and through the low gain antenna, and it tells us that it's there and that it's running the sequence that we expected it to see. And so that will be the first time that we get a direct communication without going through the orbiters. And it'll occur, depending on what path we're on, somewhere in the 5 to 6 p.m. The following night, next Monday night. So that would be our first direct path. Assuming that we do hear from the vehicle, we then transition into what I would call normal surface operations. And the big difference between normal surface operations and what we're doing now, again, is really the uncertainty. There's just lots of things that are different about this vehicle on the surface. It has different power configuration. It has the environment that it's in we don't know anything about. So there is a lot of uncertainty into how quickly we'll be able to do things. But if we go to the next chart, I wanted to give you some idea of kind of what the plan is. And you'll hear lots more about all this each day as we go along from Mike Watkins and Jennifer Trosper, the mission managers, as to what the plan is each day. But I kind of wanted to give you the big picture view of what we're going to try to accomplish as we get through the first few days. So the first day, as I said, after we land, is really just to get the vehicle stable on the surface. And it's also then to get prepared to deploy the high gain antenna. We do communicate with the high gain antenna, but it requires knowing where the vehicle is in order to point the high gain very precisely at the Earth. And so the first thing we need to do is to deploy it, and then to figure out essentially where to point it so that we can communicate directly to the Earth, and as well as send commands through the high gain antenna. The next day, we would then deploy the mast, the RSM, and that will give us the ability to take pictures with some of the cameras that aren't accessible otherwise. So that's why, for example, our first pictures are the HazCams, but after a couple of days, we should be able to take NavCam images and begin to do MASCAM images as well. On the third day, we will do a checkout of all the instruments just to make sure that they're all still functioning, sort of a very simple aliveness test for the instruments. And as I mentioned, will be our first chance to take a panorama we'll have gotten these little postcards of the area in front of the rover, but this will give us a chance to get our first 360 panorama. Then on the fourth day, we basically have a quiet day. The panorama is a big set of pictures, takes up a lot of data volume, and so we want to essentially not do a lot else other than just send that data down and have it on the ground so that we can begin to plan what to do long term with the mission. Once we get past that, then we transition to an important engineering activity that will take several more days, which is that we have a set of flight software which we've used during cruise and the landing event, but it doesn't have all of the functionality that we want to use for the surface. And so we want to transition flight software versions, basically. The flight software version that we're transitioning to is already on the spacecraft. It's already been loaded up there, but it's not running. It's not active. And so it will take us several days, actually, to transition over to it and begin to use it. If we go to the next chart then. This I kind of talked about already, but just to talk a little more about the products we expect to see as we go through this. And there have been various press releases already talking about this at some level, but just to reiterate, the main idea for the first night is to get these black and white low resolution HazCam images. And again, we expect to get thumbnails, which are very low resolution, like the 50-bit or 50 pixel by 50 pixel kind of little thumbnail postcards. And then we hope to get that first night a more like 512 by 512 pixel kind of image, again, black and white, looking out the rear of the rover. After we get through that first day, then we'll start to send down the MARDI images that Mike Malin talked about a couple days ago. That's the descent imager. We'll start sending down the thumbnails of that. So selected images as we were going down through the landing event, we'll take those pictures and send them down. The first color picture, we're actually using the Molly camera that's on the end of the mast. And we're actually sort of looking out sideways out the rover, and we'll take our first color image using it and send it down on the third day or so. And then, as I mentioned, we'll eventually get to doing the NavCam panorama, and that will take several more days to get, that's when it will start coming down on the 9th, and it will take several more days to come down. And again, this is the nominal plan. Clearly, if the vehicle is experiencing issues, or if we have other, we're trying to work through, problems, that we'll have to change this plan in response to that. Once we get beyond the first few days, then I just laid out a little bit of what's the long-term plan for the first couple of months, first 2 or 3 months. And again, I think Pete probably mentioned it the other day when he was talking, Pete Tysinger, but this is a very complicated vehicle. It's way more complicated than MER or other vehicles we've flown in the past, and so it's going to take us a while to first check it out and then to get into the science that John Gratzinger and Ashwin and everybody else wants to do. This is sort of our nominal plan. Again, it's going to be responsive to what we find. We're going to spend almost the entire month of August really checking out the vehicle, getting the first images. We will obviously be getting science data during that, but we'll also be doing engineering checkouts of the instruments, of the sampling system, changing flight software, doing other things. Hopefully by early September, we'll be at the point where we can do our first drive and have the vehicle begin to move around a little bit. And then beyond that, we'll go into the sampling where we first do a scoop sample in late September probably, and then a drill sample sometime after that. October, November is what we're expecting at this point. So I think that's my last thing on the planned activities. Let's just go to the next chart for a second. Quickly, but to finish up, one thing that people are always confused about, and so this is our effort to try to explain it a little bit, is the difference between Mars time and Earth time. I tried to give you calendar days on the previous chart to sort of tell you when we expect to get things, but obviously in reality, the rover and all of the operations team, all 700 people if you count the scientists, are all working on Mars time, where the vehicle, to be synced up with what the vehicle is doing. A Mars day is about 40 minutes, 37 minutes longer than an Earth day, and so in fact, the relative clocks or days shift over time. We land on Sol 0. And it more or less corresponds, as I said, to about 3 o'clock when we land is like 3 p.m. on Mars, and then that every day basically the relative correspondence between the Earth day and the Mars day will shift by 40 minutes. And so you can see we'll be Sol 1, August the 6th primarily, Sol 2, August the 7th. Eventually they'll drift to the point where we will, instead of having to have people here in the middle of the night to watch the rover, it'll be during the day, and that will be okay for a couple of weeks, and then it will shift back again. And so you can imagine that it's like losing a time zone every day. It gets pretty tiring. But it'll be exciting because we'll be operating this vehicle on the surface, and so I think that will get us all inspired to work on Mars time for at least 90 days is the current plan. So with that, I think I've spent my time, and I will turn it over to Ashwin to tell you about the weather.
All right. We always make you wait to the end for the weather report, just like if you remember from a couple days ago, I'll just go over why we care about the weather on Mars. There's 2 things that determine the accuracy at which we land. Basically, the size of that ellipse that we were placing in that flat area next to Gale Crater. One of them is how accurately we enter the Mars atmosphere at the top of the atmosphere. And as you heard from Arthur, we're coming in really nicely down the middle. So now, the next thing that could affect the accuracy of the landing is how well we've been able to predict the conditions at Mars in the past few years based on data from previous missions that we then use to simulate the EDL, the entry, descent, and landing into the atmosphere. We continue to monitor that. We've designed the spacecraft to basically handle all the conditions that we've seen in past years, whether they're clear or dusty, but we continue to monitor it in real time, getting data from the orbiters at Mars every day this week to make sure we understand what conditions the spacecraft will encounter as it's flying through the atmosphere and just how accurately we can expect to land. So I left you 2 days ago with a bit of a cliffhanger we had seen a local dust storm south of Gale Crater. This had the possibility of evolving in a few different ways. One thing, it could have drifted towards the landing site. That would have been kind of the worst case. It would not have impacted our ability to land safely, just maybe cause us to land less accurately than we would like, a little further out towards the edges of that ellipse than the center. It also could have disappeared. That was actually the prediction by our atmospheric scientists on our team, that it would disappear within a day or two after seeing it 2 days ago, or it could have just drifted along the south polar cap where these storms tend to form. So let's see what happened. The Mars Reconnaissance Orbiter has taken global maps of Mars for us using the Mars Color Imager, and my colleague Bruce Cantor at Mail and Space Science delivers those maps to us every morning at 7:30 or so. And I'll show you on this Earth map first, just to orient you of how we view Mars in the same map format. Again, I'll point out north of Australia there, just about Indonesia, there's a little circle drawn on the map, and that's where Gale Crater is in the same location on Mars. So now if you go to the next Mars map, this is the most current map of Mars taken 2 days ago on August 2nd. What has happened is the good scenario, where that active dust storm, which was boiling at the surface and very well defined 2 days ago, has now evolved into a fairly harmless cloud of dust, basically the poof remnants of what was that dust storm. And that dust cloud is translating. It probably will not reach Gale Crater by the time we land, and if it did, the amount of dust in that cloud is not believed to affect the entry, descent, and landing in any meaningful way. We continue to see the water ice clouds over Mars. This is a good thing. We've predicted in years without bothersome dust storms, there should be a lot of water ice clouds in the atmosphere, because a cold atmosphere that's free of dust tends to have these water ice clouds at this time of year. So the more we see these clouds, the more we like it. Mars appears to be cooperating very nicely with us, and we expect good weather for landing Sunday night. We're going to continue to look at this one more time. Tomorrow morning, we'll get some more recent data. And then I'll show you one final thing, just to show you what could have happened. We have 3 prior years of Mars data from the Mars Reconnaissance Orbiter. And what this image shows is a map taken by the Mars Color Imager 2 Mars years ago. This is from October 2008. Just at the same time we'd be landing the spacecraft on Sunday night, but 2 full Mars years ago. And you can see that there's remarkably few water ice clouds. This particular year, Mars transitioned from its colder southern winter to its more dusty southern spring and summer earlier than we would have arrived if we had landed 2 years ago. And the atmosphere warmed up, the water ice clouds disappeared, and the conditions in this year were very ripe for a lot more dust activity. In fact, days before and after this particular image, there was a lot more dust storms. And that's actually what we took into account when we designed the entry, descent, and landing capabilities for this mission. We had to be able to land in all the conditions we'd seen in previous years, and so that's what we've done. But fortunately, Mars is playing nice, and we're going to get good conditions for Sunday. I'll turn it over back to you, Veronica.
All right, thank you. We're going to open it up to questions here in the auditorium. We'll start with the news media, and then we also have our NASA social participants here today with us, and we'll take some questions from them as well. So if you would raise your hand, and we'll get the microphones to you, and please give us your name and affiliation. We'll start here first, and then we'll go to the aisle next.
Thank you. Olivier Sanguy, enjoyspace.com from France. I'd like to know, in the first data you will receive from Curiosity, will you have a sort of health check of the rover, or just a beep?
So it depends on when we hear from it. That under the best case scenario, where we see the data from in each Odyssey pass, those 2 Odyssey passes that'll be Sunday night and early Monday morning, in both cases we'll get health data from the rover that tell us how it's doing. We could have to wait until the next morning, though, depending on what happened, and both on our side as well as Odyssey. Odyssey, clearly if it has something happen that causes it to not be listening, then we wouldn't be able to get that data down. So it's very much a question of what happens as in real time as we go through the evening.
Okay.
Emily Lakdawala from the Planetary Society. I know that Mars Express is going to be recording a signal. There's been conflicting information about whether there's actually going to be any data contained in that signal. And so I'm wondering if you can tell me about that and of what use that data might be, considering that Odyssey and Mars Reconnaissance Orbiter are going to be so much closer and receive better information.
Sure. The Mars Express spacecraft will be recording essentially information about the UHF signal. It's kind of like if it's there or not, and we'll be able to see the carrier signal either be present or not in the Mars Express data. And so you are right, we are not going to get actual digital data from that from the Mars Express spacecraft. We'll get a spectrograph, if you will, of what the radio heard during entry, descent, and landing.
It also doesn't occur in real time either. We get it, it's like MRO, where we'll get it recorded. They will record it, and then they'll send it to us a couple hours after landing. So.
Okay, we're going here next, followed by Leo over here, and then on the other side.
Hi, it's Craig Cavalt with America Space and Aerospace America. Question about the DSN configuration. Which DSN station will be the prime one on the landing night when you do go over the hill, and discuss DSN antennas further as to which ones are going to be the workhorse?
So our Canberra DSN stations will be prime for EDL. We also have antennas at Parkes and at New Norcia in Australia, which will be tracking the spacecraft.
Leo Enright with Irish Television. I think probably for Steve Sell, although Richard Cook is pretty good at reassuring us over the years. I was looking at things that might go wrong last night, and so I thought I found something that I hadn't noticed before. And that's a thing called the parachute sabot. There was a description somewhere that I read last night which described this thing deploying the parachute and then recontacting with the descent stage to the point that it was quite violent and might even damage one of the radio antennae. Was I being over alarmist?
You might be mixing a few things there. We do have a parachute closeout lid, which is essentially the top of the I guess you can see it right here, the top of the thing that closes out the top of the parachute cone. That does get pushed off the top of the spacecraft when the parachute deploys, but we've done lots of analysis on exactly how that lid behaves after deployment, and it should drift off to the side. We don't expect any recontact there. I'm not sure if that's what you're referring to or not.
Good morning. Irene Klotz with Reuters. I have two questions. The first is for you, Doug. You all have done a really good job in words and pictures of describing the risk of the entry, descent, and landing, but NASA is an agency of numbers, and I was wondering if you did have a probabilistic risk assessment of landing successfully overall, and if there was any particular element in the descent that, from a numerical standpoint, from a risk assessment standpoint, is riskier than the other.
I don't think there's a single number that we can put on this. We rate this. Everybody gets to feed into the risk decision process and the risk understanding process, and so we've collectively agreed that this is as low a risk proposition as possible. But it's almost impossible to put a single number on the probability of success from the top of the atmosphere to the bottom. So, Irene, there's not really a single number. There are analyses that are done, and so you can relate those to risk in every event that occurs. But I think that, it's just such a complicated environment that I don't think that any single number is useful, to tell you the truth. Richard, do you have a different view of that?
No, I think we do, and Steve could certainly talk about it a lot more. We do simulations, Monte Carlo simulations, thousands of cases where we simulate all the different parts of particularly the flight trajectory, the flight dynamics, how the vehicle will, use guided entry algorithms and all that, and we get numbers from that. But that only represents some parts of what the potential risk areas are. It doesn't include things like will the hardware do what it's supposed to do? It assumes that all the hardware will do what it's supposed to do, but it's not, and you get a number that comes out of that, but it doesn't then roll in what's the probability that you might have a problem with the parachute or whatever. And so it's hard to point out a single thing where it all comes together in one, as Doug said, in one integrated number.
Okay, thanks. And for Arthur, could you please explain a little bit more about what that last planned data relay to MSL tomorrow night with the backup computer, exactly what that does? And for Steve, if you could give us the altitudes of the MRO and Mars Express at the time of landing. Thanks.
Yeah, actually, that activity is not a relay. It's a commanded activity on the spacecraft. It's our plan. It's been our baseline plan to activate our backup computer with a set of software that, if in the event, very unlikely, the prime computer reset during EDL, the backup computer would take over and land the spacecraft. So it's always been in the plan to do it at this time, and it's our last remaining significant operational activity.
And as for the altitudes of MRO and Odyssey, I'd have to get back to you on that. I don't have the exact numbers of those.
Okay, we're going to take a couple questions from this side of the room, and then we're going back over there. Go ahead.
Todd Halverson, Florida Today and USA Today. I was wondering who is responsible for bringing the peanuts into the Mission Control Center. And I was also wondering if one of you guys could give us an idea of what your day is going to be like tomorrow, if you have any landing day traditions or special activities that happen, during the course of the day leading up to coming into work. Thanks.
Well, on the peanuts, I think it's everybody's responsibility to bring peanuts on
Because
these
of that,
events.
we have 50 jars.
So we have plenty of peanuts.
Plenty of peanuts.
And the mission manager usually assures that we don't run out. With respect to, traditions on landing day, I think, it's traditional to take a deep breath when we finally get there and reflect a little bit on how far we've come and where we are. So I think there's a moment of joy and a moment of reflection as well.
Yeah, my version of that would be as well that usually when you get to the last day, there's not that much to do, right, other than to wait. And so usually you get a chance to go have coffee with some people on the team and to do exactly what Arthur said, right, which is to say, okay, it's been a long trip here to get here, and it's going to be an interesting next few hours. And time seems to have a weird sort of rhythm in that last day, right, where it goes real slow for a long time, and then in the last 15 minutes it goes like that, and it really goes quickly, and all of a sudden it's upon us. And so that's what will happen.
Hi, Mark Kaufman with the Washington Post and National Geographic. Editors, of course, are very eager to know when might we know that the thing has safely landed. And I know that there's the 14-minute distance gap, but what should we be telling our editors in terms of the earliest moment, the likely moment, and then I have a second question as well.
I can tell you that touchdowns at 10:31, 10:32, there is some variation on that due to atmospheric changes that change how long we might be on the parachute. But essentially, we're within plus or minus a minute or so of 10:31. And if we have Odyssey coverage throughout, if the Odyssey coverage remains all the way through, we'll be able to follow it through touchdown at that time. As Richard mentioned before, there are scenarios in which we, for any reason, might not have the Odyssey data available, in which case then Richard went through the several opportunities after that we could know what happened.
A scenario that then would be 10:45 or so, and how would we be informed?
No, the 1031 number is Earth receive time.
Oh,
so,
that's Earth received.
Yeah,
Okay.
so it will. Yeah, that's an interesting thing to point out is that we're actually watching the whole thing on a 14-minute light delay. So it actually touched down 14 minutes ahead of that, but when we find out here is 10:31.
And how would we be informed?
You'll probably be able to tell by us celebrating.
Yeah. When everybody starts high-fiving each other, that's
usually
when
a good
you'll know.
sign.
Okay.
Under the case that we don't know, then what we're going to go into is we'll have either a press conference or a report out of the MSA, as to what we think we know, and some member of the team, probably Pete, will give a briefing as to what we think we know, and then we'll wait until that next Odyssey pass at 12:30, and we'll by that point, I, by the way, have shifted to a different mission support area, so a different control room. It'll be in a different area here at JPL, but it's and the surface team will be there to sort of monitor whether or not we get a communication signal. But so that would be the next time we would hear from it is at that 12:30.
Okay, and if you would, just one other question. You had said that the entry seems to be picture perfect. Could you give us just a little bit of comparison with other Mars entries? Does this one seem to be more precise, about as precise as others? Have there been others that were way off and then suddenly, were able to be brought back in?
I think this is about as good as there is. I haven't seen one better than this one. Richard, you want?
No, I think it's exactly what you said. This spacecraft design, the way that this vehicle is designed to fly during cruise, is the same way as MER and Pathfinder before it, and because of that, they're very, very good as far as navigation. That we have a very good idea of where they are, and so on all of those spacecraft, they did about the same as far as their ability to get it to the right spot. In this case, we have the challenge of not only getting it to the right spot, but also telling it where it is, which actually makes it even more of a challenge. And so that part of it, they're actually doing even better than what we've done in the past. So.
All right, we're going down the aisle here. Go ahead.
Hi, I'm Alan Boyle with NBC News. And I wondered if you could talk a little bit about the scenario where there are no signals received and how long that search is going to continue. I think with the Polar Lander experience, that went on for a while. And then a happier thought would be having plans for MRO to take a picture of the landing site. Are there any plans to do that at a particular time?
Yeah, I guess I should talk about MPL since I remember it better than most. I think that the way we sort of look at it is that there are certainly very credible scenarios by which those Odyssey and MRO passes, in the first 18 hours might or might not happen, and so because of that, we definitely think that we can identify ways in which we would have to wait until the next morning, for example, to hear the MRO pass. The X-band, same thing, that if we, for example, had a problem with the radio, the UHF radio on the rover, it's not going to, we actually have two of them, but it's actually not going to switch over to the backup one on its own, that it would take, for several days, it would take a while to change over to the other radio. So because if, for example, we had a failure of the radio, we would certainly not hear anything from any of the orbiters. So because of that, there's a scenario in which you might say, well, we have to wait all the way until 5:30 the next night to hear from the separate system that does direct-to-Earth communications. And so those are all very credible, or certainly credible situations where we'd have to wait through that. Once we get past that first beep, from the X-band system, if we haven't heard from it in any of those communication paths, including that one, then I think that we would be definitely in the not as, in the more likely than not that we had a problem. And so it would take 24 hours, order of 24 hours to come to that conclusion. There are certainly scenarios that we can come up with, and we've got a lot of smart engineers who can think of, off-nominal paths that can get us to it taking longer than that. But frankly, I don't think they're very likely. And so I think once we get past that first day, we're definitely in the low probability category. MRO, so yeah, you asked, are we going to try to take a picture? When will we get it back? They are going to try to send it back pretty quickly after landing, and so we hope that we will get it by the time the next morning comes around. We'll have that picture, but it depends on if they got it and how long it will take them to process it. But we're pushing to try to get it that next morning.
That would be a picture of the landing site post-landing?
No, that's a picture as it's going down.
Right. Is there any
then there is a plan to actually take another picture from MRO of the vehicle, the rover on the surface, The next day, so like 24 hours later, there'll be an attempt to take that picture. So.
Okay, we're going to come to the very front of the room here.
Thanks. Jonathan Amos, BBC News. Just remembering back to Phoenix, I think there was one person in the control room who was tasked with calling out the milestones. Will we have something similar this time so that we know we can follow it?
Yes, we will. Maybe, Steve, you can talk to the
Yeah, we will have someone in the control room. Alan Chen is his name, and he'll be narrating the sequence as we go through it. He'll be calling out the tones that we'll be receiving from the spacecraft, as well as the UHF data. So he'll be the voice of mission control that you'll hear in the feed. Alan Chen. Chen, yes.
Let's see here. Let me see where the mics are. Okay, let's go here, and then we'll go back on the aisles.
Jackie Goddard for the Times of London. First, Steve Sell. I apologise if I haven't grasped this, but I just want to be clear. This all-important beep that tells us that it's down and landed, what form does that take? What do you see? Do you see a line of code? I think you said you don't actually hear a ping, and it's not presumably just saying, I'm here. What do you actually see that we're wanting to...
You asked a very technical question, but basically it's a line of code. We call them EVRs. That basically it's just almost, you can almost think of it as a text message kind of thing. They're very short, and they have a little bit of information. So the touchdown EVR will contain everything from a couple of numbers that tell us how fast it touched down to where it actually thinks it touched down, and so we'll get that information, and it'll appear on our screens. It'll also you'll see that indication on the displays that are available as part of the feed.
Do you happen to know what EDR stands for?
Oh, event record. Event record. Sorry, you can't take the engineer out of the the acronym out of the engineer. Yeah, right.
EVR.
Yeah, EV event R record. Yeah.
Okay, next. Go.
Steve, can I just follow up with Scott Gold with the Los Angeles Times? So it's essentially an either-or situation as far as when you'll receive confirmation that you're on the ground. In other words, if you have Odyssey coverage the first time, you'll receive that at roughly 10:31, and we'll see you high-fiving each other, and we'll know at that point something. If you don't have Odyssey coverage, then it's an either-or scenario, and you won't know anything for sure for another 2 hours, one way or the other. Is that?
Yeah, that if we don't have Odyssey for whatever reason at touchdown, then yes, it would be several hours till we could know anything additional.
Okay. And what might we be, continuing the effort to please our editors on a very tight deadline, what might we listen for from Alan Chen to when he offers confirmation to you that something good has been received at 10:31? What should, since we aren't in the room, what should we listen for that would give us an indication that things are progressing as expected?
They will be playing the audio. Alan's audio will be played over, whatever feeds that you happen to be watching. So you'll hear it the same time we hear it, and he'll say that the rover's been, or that we've received the signal that the rover has touched down on the surface.
Thank you.
Okay, let me go. I'm trying to get people who haven't had an opportunity yet. So we have one in the back there.
Hi, Steve Gorman with Reuters. My editors are also interested in they want to know when this thing hits the atmosphere at 13,000 miles an hour, I think you're going to be getting a beep that alerts you that that's happened. Is that right?
Yeah, that's right. The tones, kind of some major events that we'll get by tone only. We'll get cruise stage separation. Let me give you some Earth receive times on these. So around 10:14 or so, 10:14, you'll receive cruise stage separation tone for that. We should get an entry tone at around 10:24, about 10 minutes later. And then, like I said, there are a couple more along the way that we use to tell how far along the spacecraft has gotten during entry, descent, and landing. So we send out some tones when we start the turns, the bank reversals, and when we are deploying the parachute and things like that. But we, like I said in my at the beginning, the Earth will set from view of the spacecraft at some point while we're on the parachute. So at some point, about a minute or so after the parachute deployed, we will no longer be able to receive those tones, and we'll be relying on the data relay through Odyssey for the remainder of landing.
Okay, and can I just so if for some reason there's not a tone when the thing, you don't get the Odyssey's not available when the thing actually lands, and so you don't know whether it's landed or not. I believe you guys said the next opportunity for you to get some data would be at 5:30 when there's an MRO overpass, 5:30 a.m. our time?
No, it's so, yeah, so let's go through it again here. It's a little confusing because Odyssey is there and it's sending us data back in the bent pipe mode where he was saying you get the data essentially in real time. In addition to that, though, MRO is flying over at the same time and it's recording all the data.
Okay.
And so during the middle of the night, that data, after the Odyssey pass, actually, that data will get transmitted back to the Earth, and we will start processing it here on the ground to see whether or not MRO recorded the
Anything that Odyssey missed,
or if Odyssey missed the whole thing, MRO certainly could have been recording it. We just won't know until that data comes here to the ground and we process it and we go through and do the signal processing we need to do.
And how long will it take before you receive the MRO, the pre-recorded, if you will?
I think it gets to the ground in about an hour and a half after landing, and then it will take us somewhere between an hour to determine if there was a signal there, and then about 4 hours to get the telemetry data out of it that tells us what the spacecraft was doing during.
But Odyssey wouldn't have another crack at it for another 12 hours or something.
Right. So it's sort of there's an interleave set of things. Odyssey is doing its own thing. Odyssey has the pass that's at 10:30, and then another one at 12:30 at night. Right.
12:30 a.m.
12:30 a.m.
2 hours after
landing. That's right.
So is it possible that Odyssey might pick up something on its second pass at
It might.
12:30 that
Absolutely.
you still wouldn't have found out about because MRO still hasn't transmitted back to you?
That's right, exactly. So there's various scenarios by which we might find out either from an Odyssey overflight that occurs 2 hours later, or when we go back and process the MRO data, or even when we look at the Mars Express data, which kind of shows up in that time frame as well. So all throughout that night, we're getting various pieces of information, and in all of these cases, each of the spacecraft is retransmitting it a couple times, because we could also lose the data, as it's transmitting it. I mean, the orbiters sometimes have data dropouts where the data doesn't all come down, and so they're going to send it multiple times just to make sure we got all the information here on the Earth. Right. The next time the rover will try to communicate to us after that 12:30 opportunity is the next morning at like 11:30 a.m. here, where it will again try to communicate through MRO and Odyssey in a new time that it will try to communicate.
Through the bent pipe, or is that direct?
In the case of Odyssey, yes. In the case of MRO, no. It will record it and send it back.
I mean, the rover you said will next try to communicate directly to Earth?
No, to the orbiters.
To the orbiters, okay.
Yeah, its first time that it will try to communicate directly to the Earth will be at 5:30 on Monday afternoon. So almost 18 hours or whatever after landing.
Thank you.
All right. Well, let me just clarify one thing. Well, we'll be doing commentary during landing, of course, and right after landing, we will switch to the surface mission support area for that 12:30 Odyssey pass. So you will be able to see both that night, the initial one at landing and then the one a couple hours later. And let me see if there's someone else in the room who has not been able to ask a question yet, and then we will invite NASA social participants if you'd like to ask a question. So we'll go right here on the aisle.
Hi, this is Mike Wall from Space.com, and I wanted to ask a question, actually, of the guy who just walked off the stage and coughed Ashwin. This is about the Mars weather, dust storms and such. I mean, you're saying that it's never going to be a serious concern because you've sort of designed this craft to sort of weather whatever dust storm that could be thrown at it. I mean, have you ever seen a dust storm on Mars that is strong enough, big enough, conceivably, to actually imperil the spacecraft, or is it always just kind of an annoyance where it might push it off course a little bit?
Yeah, that's the analysis we did with the past years of data. The guy I mentioned, Bruce Cantor at Mail and Space Science, has spent years counting every dust storm, learning how they behave, figuring out how they evolve over time, how the winds blow associated with those dust storms. And at this season, we realized that if we were to land, right down the middle of a dust storm, we could actually get winds that could, fairly severely affect the ability to time some of the events when some of these critical events happen, because the spacecraft is sensing the conditions in real time. So there could be certain cases where a very violent active dust storm right at gale could cause a problem, but that's not typical of the season at all. In fact, the risk of an active dust storm right over gale, we realized, was extremely small. It's never actually been seen. Instead, we looked at what actually could happen and the full range of events that could happen, mostly related to dust storms along that south polar cap that push dust towards gale, and designed the spacecraft to handle the dusty years, the clear years, all those conditions. So this is a very tolerant spacecraft. It's almost putting us out of business in terms of predicting the weather. Previous spacecraft were much more sensitive to the atmospheric conditions, partly also because the spacecraft is so big. The descent stage and rover that flies the spacecraft down are very tolerant to winds at the surface, where previous landers were affected by those surface winds. So we haven't really had to consider winds at the surface much at all. We really just care higher up in the atmosphere, where we're doing the guided entry and where we're timing some of those events like the heat shield coming off and initiating the powered descent.
Okay, here on the aisle, thanks.
Henry Bortman with Astrobiology Magazine. Steve, you described during the descent stage the rocket-controlled back and forth motion of the spacecraft. And correct me if I'm wrong, but that's not only to more accurately position the craft for landing, but it's also kind of like doing switchbacks and controlling or targeting a specific rate of descent?
Sure. So when we first enter the atmosphere, the first thing we do is we enter what we call range control. And if you can demonstrate briefly here, instead of flying sort of straight into the atmosphere where the nose of the spacecraft is kind of pointed straight ahead, we actually fly in with a little bit of a tilt. And that gives us a lift, or we call it a lift vector, which allows us to, as we turn the spacecraft, it will steer it back and forth across, it will steer it in through S-turns. Now, the only reason we do the turns is because if we want to fly higher in the atmosphere where it's less dense, so we slow down slower, we actually turn the lift up. That'll make the spacecraft fly a little bit higher where the air is thinner and we won't slow down as quickly. And if we need to dip down into the denser atmosphere, we turn the lift to the side, the spacecraft will sink a little bit. And the fact that we have to turn the lift to the side in order to sink the spacecraft causes us to do these turns. And so we don't want to get too far off course. As we start to drift off to one side, we'll flip over and fly the other way. And we just keep sort of flying back and forth. All the while, what we're actually controlling is how high or low we're flying through the atmosphere to stay in a certain range of deceleration to bring us to a stop over the target. I hope.
All right, I'm going to see if there's anyone from the NASA social event that would like to ask a question. We have one here in the front. If we can get a microphone to her, raise your hand a little higher so they can see you. And then give us your name and where you're from.
Hi, I'm Rachel Sanders. I guess I'm from the internet. So you were talking about the landing of this, and so can you talk a little bit about how it tries to land in that ellipse, how it does any hazard avoidance, where it decides to land and things like that? Thank you.
Sure. Basically, we load on board the spacecraft a target, so a latitude, longitude on the planet that we're trying to fly to. And right before entry, descent, and landing starts, you may have heard us talk about entry parameter updates that we do periodically. And all we're doing there is we're telling the spacecraft, when you start entry, descent, and landing, you are here. So you can imagine you're given a map, and we're putting the dot on the map of where the spacecraft is starting. And so on board, it's constantly sensing how much it's turning and how much it's slowing down. And so it's sort of calculating where it is on that map and trying to fly itself to the target that we have preloaded. Now, we don't do any hazard detection and avoidance. We sort of did that manually ourselves by placing the ellipse in an area where the number of rocks or slopes that would exceed the capability of our touchdown system, where there was low probability of encountering stuff like that. So we find a nice safe place to put the ellipse down. So we put it down, we pick the X marks the spot, and we tell the spacecraft fly to that X.
All right, we have time for one more question, and let me see if there's, you have not asked a question yet, correct? Okay, let's take you, and then others, you can come up after the press conference and ask some more questions.
Brad Snoder, Western Washington University Planetarium in Bellingham, Washington. Do you have an idea in mind for naming the rocks in the landing site?
Yeah, it's a good question. I'll start just with some of the bigger features. Gale Crater was named by the people who name these things on planets, the International Astronomical Union and the other mappers. He's an Australian astronomer who lived a long time ago. We didn't come up with that name. Also, that same body has named the major features on Mars for the historical, what they call albedo features, going all the way back to telescopic days. They're bright and dark patches on Mars. And the closest one of those features to Gale Crater is called Aeolus. And so the official names really of the mound inside of Gale Crater where we're going is called Aeolus Mons, Mount Aeolus really in Latin, I guess. The team has also informally named that feature inside of Gale Crater Mount Sharp in honor of Robert Sharp, who was a planetary geologist at Caltech, and really one of the founders of planetary geology, who brought Earth geology to Mars in the early days of the Mars Mariner missions. Once we get on the surface, we'll start naming those smaller features as well. And the team is still working through exactly how that'll happen. What they have done, as John Grotzinger told you a few days ago, is divided the entire area where we're going to be exploring up into these quads, this grid pattern. And each scientist on the team who has been looking at that grid will come up with a naming scheme for features in that area. And that's sort of how we'll go about it. I don't have any of those for you right now, but that's something that we'll be working on.
Okay, I'm told we have time for one quick question and answer. So I'm going to go with the hand I saw first, and that was over here on this side, all the way up on the aisle. Thanks.
Irene Klotz with Reuters. Ashwin, could you just describe the other, I guess the scene at Mars? As you said, it's going to be 3:30 in the afternoon there. What's the temperature? What do you expect the winds to be? What color are those ice clouds? Thanks.
Sure. Yeah, based on our orbital reconnaissance, we believe that there'll be a little water ice haze. So it'll be a late afternoon day on Mars when we land. We won't see this right away with those black and white pictures, which are more pointed to the ground. But in the next few days, we'll be inside this deep topographic hole on Mars. Gale Crater is a hole punched into the surface of Mars. And as such, there may be these water ice clouds that a haze overhead. The sun will set, on the rim of the crater, maybe a little earlier than it does in other places, because we're inside this hole. We'll be looking out towards the mound. The skies will be pink, of course. We are in an equatorial site, so we won't have a big seasonal range of extremes over the year. That's one thing that actually worked out pretty nicely with this site. But it is cold. It's Mars. So we expect temperatures maybe at plus 10 Fahrenheit or so in the day, and maybe minus 100 or so Fahrenheit at night. So it's a good swing of temperatures. And the spacecraft, of course, and all of its instruments had to be designed to withstand all these things. The winds are going to be interesting. In fact, our meteorology team is getting more and more excited about measuring the winds with this rover at this site, because unlike other flat sites we've had to land at before, the topography itself is going to be driving the winds at this site. There's going to be winds coming down from the Gale Mountain. Basically, these are katabatic winds that form because of the topography as air heats up differently. And so this wind will come down the mountain in the afternoon and rise up the mountain in the night. Won't be violent, no harm to the spacecraft, but we'll be able to measure really how the winds swirl around inside this crater. The final thing is you may notice that there's dune fields around the Mount Sharp. And one of the interesting things we'll be doing is trying to understand how that complex wind field inside this crater has resulted in the geologic story at Gale. How has it eroded the mound? And how has it moved these dunes around that we see today?
All right, that's going to conclude today's news conference. Thank you so much for joining us. I'll give you a little bit of the schedule for tomorrow. We will be back at 9:30 a.m. tomorrow Pacific time for our final pre-landing briefing and a new update on the status of the spacecraft and landing. At 3 p.m., we invite you to join us for a chat with NASA Associate Administrator John Grunsfeld and JPL Director Charles Alachi. And our commentary will begin tomorrow evening at 8:30 p.m. Pacific Daylight Time. We hope you will join us for that. Thank you so much for joining us, and broadcasters, please stand by for a replay of today's images. Thank you.